Hello everyone, welcome to Merrimack STEM Academy. Today we're going to talk about collision theory. Many chemical reactions don't occur instantaneously. Some reactions occur very quickly and other reactions occur much more slowly, like rust forming on metal. The speed of a chemical reaction is measured by how fast the reactant molecules are being used up or by how fast the product is forming. Chemical reactions tend to start fast and slow down over time as the reaction reaches equilibrium. So, what factors affect the speed of a chemical reaction? Without further ado, let's get into it. First, how do chemical reactions occur? You might assume that two particles can come into contact and bam, a molecule is formed. Really, in most cases, it's not that simple. Collision theory explains how chemical reactions occur. The first part of collision theory states that reactant particles must collide. Reactions can't happen and chemical bonds can't be broken and reformed if reactants don't collide. Second, this collision must occur with sufficient energy so the bonds in the reactant molecules can be broken. Finally, the molecules must collide in the correct orientation for the bonds to reform. Let's go into more depth about each part of collision theory, starting with the fact that molecules must collide for a reaction to occur. The number of collisions that occur affects reaction rate. Also, if there are multiple reactant molecules, all of the necessary reactant molecules must collide in order for the reaction to occur. Reactions must also occur with sufficient energy to overcome the energy barrier and break existing chemical bonds. This energy required for a reaction to occur is called activation energy. All chemical reactions have activation energy, including exothermic reactions. For example, there must be sufficient energy present to break the bonds in N2 and H2 in order to form ammonia. Molecules must also collide in the correct orientation. For example, when nitrogen monoxide and ozone collide in this orientation, the chemical bonds cannot be broken and reformed. The reaction doesn't occur. However, in this other orientation, the bonds can be correctly broken and reformed, so the product is produced. The fact that collisions must occur in the proper orientation and with sufficient energy means that not all collisions result in a chemical reaction. In fact, only a certain percentage of collisions are successful. The percentage depends on the chemical reaction and the conditions the reaction is occurring under. The number of collisions that occur and the percentage of collisions that are successful determines the rate of the chemical reaction. Let's talk about some of the factors that can affect the reaction rate. First, temperature. Temperature affects both the number of collisions that occur and the percentage of collisions that have sufficient energy. At a higher temperature, the molecules will have a higher average kinetic energy. Kinetic energy is related to velocity. So, at a higher temperature, the particles will move faster and have more collisions. Generally, at higher temperatures, the reaction will occur faster. Also, at a higher temperature, the molecules will have more kinetic energy. That means that at a higher temperature, a greater percentage of molecules will be able to overcome the activation energy. As a result of both of these factors, in general, the higher the temperature, the greater the reaction rate. Temperature and reaction rate are directly proportional. The concentration of an aqueous solution also affects reaction rate because it affects the number of collisions that occur. At a low concentration, there are fewer reactant molecules, so collisions are less likely to occur. As a result, the reaction rate will be lower. On the other hand, at a high concentration, there are many reactant particles. Collisions are more likely to occur, and they will occur more often. So, as concentration increases, the reaction rate will most likely increase as well. They are directly proportional. Next, let's talk about pressure and volume. Like concentration, pressure affects the number of collisions. At a low pressure, the reactant particles are colliding with the walls of the container with less force. There are fewer gas molecules per unit volume of the container, so fewer collisions will occur. At a higher pressure, there are more molecules per unit volume, so more collisions will occur. In most cases, the reaction will occur faster at a higher pressure. One way to change the pressure is to change the volume of the container. Volume and pressure are inversely proportional. As one decreases, the other increases. For example, let's say we have two identical containers of a gas. If we decrease the volume of the container on the right, the pressure will increase. As a result, the number of collisions will increase. So, decreasing the volume of the container increases the pressure. As pressure increases, the number of collisions increases, and as a result, the reaction rate increases. Next, let's talk about the surface area of a solid, which also affects the number of collisions. Say we have two identical zinc cubes and we want to dissolve them in hydrochloric acid. We're going to leave one cube as it is, and we're going to break the other cube into smaller pieces. The zinc cube on the left has a lower surface area, whereas the zinc on the right has a higher surface area. When we place these cubes in hydrochloric acid, the acid can only react with the molecules that it can collide with. To illustrate, the acid can react with the molecules on the front of each face of the cube, but it can't react with the molecules in the center of the cube. The cube on the left has lower surface area, so fewer zinc molecules can react with the hydrochloric acid. For the broken up cube, it has higher surface area, and more zinc molecules can be accessed by the hydrochloric acid, so there will be more collisions. Because of this, surface area and rate of reaction are directly proportional. As surface area increases, the reaction rate will increase as well. Concentration, pressure, and surface area are very similar, except they are relevant for different phases of matter. Concentration for aqueous solutions, pressure for gases, and surface area for solids. They all affect the number of collisions, and as they increase, the rate of reaction increases as well. Next, let's talk about catalysts. Catalysts increase the rate of a reaction by decreasing the activation energy. Reactions with catalysts will have a lower activation energy. This is a graph of the kinetic energy of reactant particles. If there is a catalyst, the activation energy will be lower than it would be without a catalyst. As a result, more particles will have sufficient energy to react when a catalyst is present. So, a greater percentage of collisions will result in the chemical reaction occurring. A catalyst increases the rate of a chemical reaction. The nature of reactants also affects the rate. What does the nature of reactants mean? Basically, more similar reactants will react faster. For example, let's look at a combustion reaction that occurs between candle wax and oxygen. Candle wax is solid and oxygen is a gas. For the reaction to occur, the wax must first be vaporized, which takes time and energy. Once the wax is gaseous, it can react with oxygen. On the other hand, if the reactants are both gaseous, this extra vaporization step isn't needed. Let's look at another combustion reaction, except this one uses propane gas and oxygen. Both reactants are already gaseous, so they can react much more quickly. In general, more similar reactants will react more quickly. Another thing that's important to consider is the chemistry of the reactants. The reactants will affect how quickly the reaction can occur. To illustrate, let's take a look at three similar gases: ethane, ethylene, and acetylene. Ethane has a single carbon-carbon bond, ethylene has a carbon-carbon double bond, and acetylene has a triple bond. The triple bond of acetylene is much stronger than the single bond of ethane, so breaking this bond in a chemical reaction would require much more energy and occur more slowly. It's important to think about the reactant species involved in a reaction. Let's review. According to collision theory, in order for the product to form, reactant molecules must collide with enough energy in the proper orientation. There are several factors that can increase the reaction rate and cause the reaction to occur more quickly. Increasing the temperature generally increases the rate. Increasing the concentration of aqueous reactants, the pressure of gaseous reactants, and the surface area of solid reactants also makes the reaction occur more quickly. Adding a catalyst lowers the activation energy, which increases the rate of the reaction. Reactions where reactants are of similar nature will generally occur more quickly. For example, a reaction between two gases will probably occur faster than a similar reaction between a solid and a gas. And, of course, we always want to think about the chemistry of the reactants and products. now we're going to put your knowledge to the test and see how much you've learned. Pause the video here and answer the questions as best you can. The first question asks, why aren't all collisions effective? Well, according to collision theory, 3 things must occur for a collision to be successful and form a product. Those 3 things are that a collision must occur with sufficient energy in the correct orientation. Only a percentage of collisions are effective because the collision must occur in the correct orientation and have sufficient energy. Not all collisions have these 2 things. Under which conditions would you expect a reaction to occur more quickly? When a catalyst is present or when a catalyst isn't present? Well, as we talked about, a catalyst lowers the activation energy, so more molecules will have sufficient energy to react. The reaction will occur more quickly when a catalyst is present. Next, a reaction at 30 degrees Celsius or at 200 degrees Celsius. The reaction will occur more quickly at 200 degrees. At a higher temperature, the molecules will move faster, so there will be more collisions. The molecules will also have higher kinetic energy, so more of the molecules will have enough energy to react. Part 3. A reaction with 1 mole of gas in a 1 liter container or 2 moles of gas in a 3 liter container. We are assuming that the temperature and everything else about the reaction is the same. So let's look at the amount of gas in each container. In the left container, we have 1 mole per liter. In the right container, we have 2 moles per 3 liters, or about 0.66 moles per liter. The left container has more gas per liter, so it will have a higher pressure. As we discussed, the higher the pressure, the greater the rate, so the answer here is 1 mole of gas in a 1 liter container. Last but not least, if you're trying to dissolve a metal in acid, what are some ways you could speed up the reaction? There are lots of possible answers here. You could break the metal up into smaller pieces, which would increase the surface area of the metal and allow it to react with the acid more quickly. You could increase the concentration of acid. You could also use a catalyst if one existed for this reaction. We also want to think about reactant chemistry. We probably want to use a strong acid, like hydrochloric acid, instead of a weak acid, like acetic acid. Those are just a few possible answers, and there are many different ways to affect the rate of a reaction. And on that note, congratulations, you've survived collision theory. Thank you for listening. Leave us a comment if you have any questions and let us know if there's a topic you want us to talk about next. Please like this video and be sure to subscribe for more videos about chemistry, biology, and everything STEM related.